Okay, welcome to our lecture 8, which I happen to check the syllabus. I think my numbering of the lectures is a little bit different from the numbering in the syllabus. That's partly because the syllabus started off at 0 and I didn't. But at any rate, this is the 8th time that I'm going to talk about something meaningful in class. We're going to start our discussion of multiple reactions, which is nice in the sense that it lets us get much closer to reality because it's very rare that we only have one reaction going on, although there are times where that happens. It's also nice because it sort of tacks on to exactly the same stuff that we've been learning up until this point. We just do it a few more times for each reaction. The downside to multiple reactions is it's hard to get a lot of progress made if you're doing it by hand. I will briefly review the way that we learned multiple reactions in 100, where we would use an extent of reaction to figure out what was happening. But if you want to do anything with profiles in terms of either time or space when we get to flow systems, there's not a lot of progress that you can make by hand with multiple reactions. Most of these you'll find have to be solved in MATLAB. But on this particular homework, the next one that's going to get posted on Wednesday, there will be a few on there that you can make some progress by hand with using the extent of reaction from CENG 100, because we'll just be looking at what's there to start and what's there when we're all done. The relevant sections in the book are most of Chapter 6. Again, you can, if there's anything to do with flow in any of those sections, because they sort of mix them together a little bit, we're obviously not concerned about flow systems right now. Particularly figure 6-5 is a nice flow chart of how do you solve a multiple reaction problem. Again, some of the terminology in there is for a flow system, but if you switch the F with the N, then it looks just like a batch system. With just what we're going to cover today, you'll be able to handle all of homework 4 once I post it. I want to make sure all my references are correct in 4. Your homework 3 is not due till Wednesday anyway, so you've still got time to finish up homework 3. At the end of lecture today, we are moving a little bit faster than what we had in the syllabus, which is good, so we'll be able to have a bit of a breather on Friday to work through one of these problems in a little more detail, more like we did on Wednesday where we actually set up the code and solve it. And then at the end of the lecture today, I'll briefly talk about the projects that are available on Triton Ed now that you can look at. We don't have all the tools. Well, I'll talk about the projects when we get to the projects. So today's multiple reaction discussion is on the material balance side. On Wednesday, we'll talk about the energy balance, how we have to modify that to handle multiple reactions. Today, we're just worried about the material balance side. So the way that we learned things in CENG 100 was obviously we needed to start with some reactions. Normally, they were pretty arbitrary. We can make them more or less whatever we want. I'm going to assume that all of these are reversible, but it's not uncommon to have a mixture of reversible and irreversible reactions. There's no reason that they have to be all reversible or all irreversible. So we have some network of reactions. If you want to look, there is some terminology associated with multiple reactions in terms of what's a series reaction, what's a parallel reaction. It's mostly jargon that you would have to learn with. I'm not going to use any of that jargon because if I don't tell you that those are series and parallel reactions, it doesn't change the way you're going to solve it anyway. So it's just more terminology that doesn't really contribute to being able to approach and understand the problem. If we were solving this in CENG 100, and you're going to do this a couple times on the homework, so you might want to review it in more detail when you do the homework, we would do this by writing an extent of reaction, squiggle or xi or xi, for each one of these reactions. So we'd have squiggle 1 through 3. All right, so we would number each of these reactions sort of in our head as 1, 2, and 3, and write an extent of reaction for each one. If we wanted to know how the moles of any of these things changed over the course of the reaction, remember in 100 all we knew was that Stoich table. We couldn't plot anything like a profile except in limited cases. But the Stoich table was enough to tell us what would happen at the beginning of the reaction and what happens at the end of the reaction. If we wanted to know how any of these moles change, we would say that the change in any of moles of species I is equal to the sum of the stoichiometric coefficients of species I in reaction J multiplied by the extent of reaction for reaction J. So J here is how many reactions you have. They run from 1, your book uses the letter Q for the total number of reactions. So in this case, Q is 3. You can call it whatever you want. And that would usually set up a big set, well, not a big set, 3 equations that you needed to solve simultaneously. So we would have something, somehow or another, we would have to solve for all of the squiggles. Right, so we might say the conversion of something has to be some percentage, and the selectivity had to be something, and the yield had to be something, or we would just give you enough information in the system itself to figure out analytically what all of those squiggles are. This method still works. There's nothing wrong with that method. If you use that method in this class, you have to get the same answer that you'll get through MATLAB, right? It's a material balance. It has to give you the same answer. So you can always use that to check whatever your math is that you're doing with an ODE, which is helpful because if you make a typo in an ODE, you might still get the ODE to run, you just have no way of knowing whether or not it's accurate. This is an independent way, well, not fully independent, another way for you to check your math, to figure out whether or not you're getting what you should at the end of the system. Usually it only works for isothermal systems because those expressions get really ugly for non-isothermal systems, which at that point you might as well just solve the ODE. So you're going to review that system in the first couple of problems of your homework just so that you recognize that those still work. In general, we don't solve problems like this, we solve the differentials. Because we normally have so many reactions that it becomes unwieldy to try to write all those equations for a squiggle. As opposed to writing the differentials where we just tack one onto the other in a pattern that we're about to see that extends to any number of reactions in a pretty logical way. So the general approach that we have, let me make a note here. This was the method that you learned in CENG 100. So you will get to practice that. But we're going to look at a different method because we can actually solve ODEs in here with MATLAB. And so that approach consists of about 4 steps. So the first step is probably the easiest one, which is to number your reactions. Not surprising you had to do that for 100 as well. So J just equals 1 to 2 all the way up to Q reactions. Your book is in the bad habit of switching J and I. Sometimes I means species, sometimes I means reaction. Please try to correct me if I switch it up. I always want I to be species and J to be reaction. If I make that mistake, please let me know. Your book, depending on which chapter you're in, switches it around. I don't know why. Contact Dr. Vogler. He wrote it. The next step is an extension of what we learned in, I think, week 1 or 2, which is to write all your rate laws. So when you have to write a rate law, you're going to get 1 per reaction. And again, for this class, we're going to assume that all of our reactions are elementary. So as soon as you're given a reaction, you can immediately write down what the rate law is for any of those reactions. The general form for the, well, what's that? You don't need that in your notes. The rate of, I'm going to call it consumption with that negative sign, of any species I for reaction J is any rate constant K sub J, that's a little k, not a capital K, times some function that we saw before of CA, CB, et cetera, all of your concentrations, I guess up to concentration C sub I. And if you have any equilibrium coefficients, those are going to be equilibrium constants, those are going to be inside there. There could be temperature effects inside there, Arrhenius A's and E sub A's. But we saw for elementary rate laws, this part is pretty straightforward to write for reactions. Yeah?
Is that an equilibrium K or a rate K?
That K is the rate K that sits out front. I put the negative sign on there. Remember, the negative sign is only for the reactants. It's just we're in the habit of always writing those rates for the reactants, which is why the negative is on there. It is really important when you're doing multiple reactions to keep track of your signs. There is no one way to do the signs other than to do them correctly. You could write that as a positive if you want, and all your math will still work out as long as you keep track of them in the next step, because the next step, step 3, is to write the net rates. So the net rates are for each species. So we start off writing something about all the reactions, and then we write something about all of the species. We start off with the rate law for each reaction. Now, once we have one of those for each reaction, notice I left the I in there because it could be for any of the species. You only have to write it down for one of them. Typically, you will find yourself writing it for species A, but species A may not show up in all of your reactions. So, for example, in this set that I have up there, if you look at reaction 3, there is no A that appears inside there. So A can mean different things in different reactions. It's whatever species is most important in that reaction. It doesn't have to be literally the species A in every reaction, because A won't be in every reaction. And you can pick any of them to be species A. Usually there will be one that's fairly obvious. In a case like this, there's only B, so we would only end up writing it as B. So just keep in mind that this concept of A, maybe ignore the letter A for now, and think of it as write the rate of reaction in terms of the most important species rather than in terms of A, because A may not appear in all of your reactions. The net rates for any species are pretty easy. The rate of either generation or consumption of species I is just equal to the sum of all of those rates of I and J from the first reaction J equals 1 to the last reaction Q. I kind of squeezed that in there, but there it is. So this step requires only the reactions. You write 1 for any of the important species. This step, you write the net rates for all species. It is sometimes possible that whichever rate you wrote up here is not explicitly written when you come to this step. So we need that stoichiometric relationship that we saw before. This step usually requires that thing that we saw, which was R sub A in reaction 1 over minus A in reaction 1 is equal to R sub B in reaction 1 over the stoichiometric coefficient of B, et cetera, all the way through C and plus C sub 1. Right, so very often when you get to the point where you're trying to write the net rates for all species, you've only got one rate for each equation, or each reaction, but there are multiple species in that reaction. So you'll have to use this stoichiometric relationship in order to convert from whichever species you're talking about in the rate you wrote to whichever species you need for the net rate. Because you need a net rate for all of the species, even though you probably only wrote it for one. There is one of these, by the way, for each reaction. That's why there's a 1 after each one of those. The more general way to write that, instead of a subscript of a 1, which I will try not to erase, if you put a subscript J on each one of those, right, that's the more general way, because you have J reactions, so you have J sets of these stoichiometric relationships that say, for so-and-so molecules of this, I consume or create so-and-so molecules of the other. So very frequently, in fact, almost every time you're going to need one of these for every one of those, for every net rate. And then there's one last step, which is really easy to write, less easy to do, which is solve. Do you know what Feynman's algorithm is? Feynman's algorithm for solving problems, he had 2 steps. The first step, no, it was 3 steps. The first step was write the problem down. The second step was think real hard, and then the third step was write the solution down. And that was his algorithm, and it worked for him. There are 2 types of differentials that we usually solve for the material balance. You should be able to solve either one depending on the amount of information that's given to you in the problem statement. Usually there is not much of an advantage of solving one over the other. One is to solve the material balance in terms of moles. So here, if you happen to know the number of moles that we're starting, for each one you can do that. Because so many of our rates are expressed in terms of concentrations, the more common one that you'll end up using is in terms of concentration. So dCi dt is the rate of I with, again, some initial condition. Right? Assuming you at any point know, for example, the volume, there's really no difference between solving these 2 equations. You can always get the other one based on whichever one you did choose to solve. This almost always has to go into MATLAB. Why does this have to go into MATLAB? Other than the fact that this R sub I is really complicated, you have a differential for every species. Right? So if you have species A, B, and C, you have dCA dt, dCB dt, and dCc dt. And you typically have to solve them all at the same time because your rate laws depend on the concentrations of many, many different species. You might get lucky if it's irreversible and there's only 2 species, then maybe you could solve it by hand. But in almost all cases, because multiple reactions are also reversible, you just got to solve them all at the same time. There's no shortcut, there's no amount of algebra that you can do to make it look easier. Although you will see your book pick out like half a dozen examples where, oh, if you happen to have this case, you can do it by hand. That makes it look like you have to memorize those 6 cases so that you can solve them by hand, when really those are, in the entire blob of problems that we can solve, your book spends an enormous amount of time in that dot down there, which is not this dot. This one. Right? These are all the problems that we can solve, and it's many chapters on those. Whereas the general approach of just solving the differential directly can solve almost all of these problems. So, for that reason, we will tend to use MATLAB semi-frequently to solve these problems. So let's look at how would we apply this approach to this set of equations that I've got up here. So we've got 3 reversible reactions with A, B, and C. So we're going to perform each one of those steps. I already performed step 1, right? Step 1 was to number the equations. So we've already got reaction 1, reaction 2, reaction 3. I actually do recommend that you put the little numbers on there because when you get into multiple reactions, it's sometimes easier to just keep track of numbers than try to every time think of which one was first and second. Routines can be helpful here. So we already did step 1. Step 1 was we have J is equal to 1, 2, and 3. Step 1 is done. If we go to step 2, we have to write a rate law, 1 per reaction. We're just going to pick whatever the most relevant species is for each one of those reactions. So if we look at the first one, we don't have much of a choice, right? We're going to write it in terms of A because it's the only reactant. And similarly for 2 is C, and for 3 is B. So if I want to write I'm going to keep flipping back and forth. I hope you have it on your page so you can see it. Instead of doing the copy-paste thing, because I know that frustrates everybody. If we want to write those rates, this is step 2. The first one we're going to write is the consumption of A in reaction 1. The rate constants K are going to get whatever number you have for that reaction. There's just going to be 1 per reaction. As you saw in your first homework, technically you can define different Ks for different species. In most cases here, we're just going to subscript it as 1 because I'm just going to give you a single K for a reaction. If this is reversible, that reaction was A goes to B, So we would have C sub A minus C sub B over C sub C over our equilibrium constant Kc. Make sure you put the coefficients on your Kc as well. Right? Each reaction is going to have a different equilibrium constant, so there's going to be a Kc1 sitting up there. For our next one, we have, in terms of C, so we'll have minus R sub C for reaction 2. This is going to be whatever the rate constant K2 is. For this one, we have C sub C minus C sub A squared over capital K with my little caps, C sub 2. If you find it easier to reverse the direction of that reaction, it can be done, right? There is nothing wrong with writing it like that. Typically, if you choose to reverse the direction of the reaction from the way that it was given to you, you also have to switch the K that you're using. Because the K that we typically use here, is that the forward or the backwards K? Forward. That's always the forwards K, right? If you know capital K sub C from something like EQ Calc, then you can always calculate the backwards based on the forwards. But usually it's much easier to just write it in the way that the equation was given to you, rather than, for example, if you wanted to skip around and say, well, I started off with A in the first one, how come I can't write A in the second one? You can write A in the second one, it's just sometimes it's easier to write it in terms of C. Yes?
Why the concentration of A squared?
Did I not write 2? That was supposed to be a 2A. Oh, okay, yeah, here, erase that, put a 2A on there. I don't know, I have to make an erasure now. Would you rather have it go to 2A or A and me fix the CA on the other side?
Go to 2A.
2A, let's do 2A. We're not going to solve it anyway, so it doesn't matter. But we'll have it go to 2A just so that you see an example of stoichiometry that looks a little bit different. Thank you. Yes, that should be 2A. If it were not, then it would have been that, just C sub A. But it is, so it's CA squared. And then we have a rate for the last one, which is minus R sub B for reaction 3. Remember, if you're given a reaction, the only time you should leave the stoichiometry alone is when you're writing the rate law. So since we're writing a rate law right now, we're just going to leave the stoichiometry the way that we gave it. The reason we do that is presumably somebody gave you a K to go along with that, the lowercase rate K. Those lowercase rate Ks are always based on a particular stoichiometry. And so if you were given a stoichiometry and a K to go along with it, that K is supposed to match that stoichiometry. So we never change the stoichiometry when we're dealing with a rate law. So this one would be K3, and now we have 3B is reversible to 2C. So we have C sub B cubed minus C sub C squared over K sub C for reaction 3. So that's all we do for step 3. It does not matter which species we write. Pick whichever one is easiest and write down one of those for each reaction. So just in case it's not clear, those subscripts there, that was for reaction 1, this was for reaction 2, and this was for reaction 3. This tends to be the second most tedious part. Usually you have more species than you do reactions, so this is somewhat straightforward, but you have to do it pretty much every time. The next step is the part that tends to be the most tedious because you have to be very careful about how your signs go. Fortunately, if you follow exactly the same procedure every time, it sort of takes the thinking out of it and lets you use the equations as you've written them here to take care of the signs for you. So step 3 was to write the net rates. And we're going to do it once for each species. So let's start off with species A. The easiest way to start out writing net rates is to assume that that reaction or that species shows up in every reaction. So if I want to know the net rate of A, I have 3 reactions. So there could be some R sub A in 1, some R sub A in 2, and some R sub A in 3. right? That's the worst case scenario, is I could be creating or destroying A in all three of my reactions. After you write it like this, the next step is to apply that stoichiometric relationship for each one of those reactions. So my first step is to figure out what is R sub A1. So I'm going to flip back to my previous set of equations over here. The first thing I'm going to do is find out, does R sub A1 show up here? Well, we'll get to it in a moment. Does R1 show up there? Yes, it does. Great, I don't have to change anything, right? I already wrote down R sub A1. I can just write that down again. R sub A1 is going to be R sub A1. Yes, that sounds overly ridiculous, but we're going to write it anyway. Now we're going to find out, does R sub A show up in reaction 2? No, that's already blue. Let's use green. Does A participate in any possible way in reaction 2? So I look over here at reaction 2, way back. Yes, A does show up in reaction 2, except now it's showing up as a reactant, or sorry, as a product instead of a reactant. So because it's not part of the form that we wrote, right, we look over here and we see, well, our rate for reaction 2 is in terms of C, but we need to worry about A right now. So we need to use our stoichiometric relationship to convert from rate of C in reaction 2 to rate of A in reaction 2. So the rate of C in reaction 2 over its stoichiometric coefficient, which is -1, is equal to the rate of A in reaction 2 over its stoichiometric coefficient, which is +2. So this is the one that I'm after here. Right? And so now I see from this stoichiometry that if I want to write the rate of reaction of 2, it's going to be equal to -2 rate of C2. That's the term that we're going to end up writing in the next step. So the first step of step 3, sub-step, was figure out, does that species occur in the reaction that you're interested in? Second step was write the rate in terms of that species. So you'll typically have to use these stoichiometric relationships to do so. So I'm going to take that -2 RC2 and put it over here. So now we have -2 RC2. And now I do the same thing for R sub A3. So does A show up in reaction 3? Nope. Great. We get a 0. Once you get used to the pattern enough, then you don't have to keep writing zeros. But in this way, you can go about something in a very systematic approach to figure out whether or not something is being created or destroyed in each reaction. So then when we would actually go to write these rates down, R sub A1 is the one that we wrote. So R sub A1, I'm going to deliberately introduce a mistake, is K1 CA minus CB CC over KC. Actually, with the colors, let's do colors. I can do colors. Don't worry, it's exactly the same thing if you don't have colors. There, now it's colors. This was supposed to be C sub A minus C sub B, C sub C over KC1. So does it get positive or negative? Negative, right? We have, when we start off on line 1 here, we're just adding up all the rates, right? The rate total is the sum of the rates. Underneath it, we have written that rate in terms of all of the species that we actually wrote a rate law for. Now we have to apply those signs because when we wrote the rate, by convention, we tend to put this negative sign sitting out front of each one of these. Right? So we're not writing the rate of C2, we're writing minus the rate of C2. We're not writing the rate of A in reaction 1, we're writing minus the rate of reaction 1 in terms of A. So over on this next one, we need to not forget the negative. and then we have a minus 2 times rate of C2. Rate of C2 was K2 times C sub C minus C sub A squared over KC2. But is that the plus or the minus of the rate? That's the plus, right? We actually have minus RC2 written over here, right? We have this little negative sign sitting here. So that negative sign is going to cancel out with the other negative sign. Right, now it's getting confusing. So this negative is actually positive. How can we check whether or not this is consistent? The best consistency check you can have in terms of signs is to figure out, do I expect if the reaction occurs in the way that it's written, should this concentration or the rate of A be positive or negative for a particular reaction? Is it listed as a product or a reactant? So according to the first equation here, the rate is negative, right? This entire term has a negative sign sitting out front, which suggests that in the way that the reaction was written, A is being consumed in reaction 1. Is A being consumed in reaction 1? Yes, the way that it's written for our reversible reaction, A occurs as a reactant. For the next one, we look at this sign on the green and say, all right, according to that sign, A should be showing up as a product in reaction 2 because there's a plus sign up here. So we look back at our reaction 2 and we find out, oh, okay, good. A is indeed showing up as a product. So you can use a little bit of sanity check here to make sure that those signs are following whether or not things are showing up as products and reactants. There should never be there's no trick that ever occurs in here where something as a reactant suddenly shows up as a negative over here. Right? We don't write things like that. This is the convention that we always use. So those signs should always end up working out for you when you're done. If the thing shows up as a reactant as written, then it should be negative. If it's a product, then it should be positive, with the little stoichiometric coefficient as needed. Right, so we have all of that and then plus 0, obviously. There is no 0 term. And that's it. That's the full rate for A. If we want to write the differential equation for A, the differential equation for A just looks like dCA dt is equal to the rate of A, which is equal to the rate of A in 1 plus the rate of A in 2 plus the rate of A in 3. Which I'm just going to replace with colored boxes. So we had that big term in purple, or fuchsia, whatever you want, the big term in green, and then 0. Why did I put the box there? I put the box there because most of the time you're going to write it in MATLAB anyway. You're going to have to start out writing it by hand, but that pink term can be its own line in MATLAB. Remember I said it's usually a lot easier to let MATLAB do that algebra for you. If you look at like the coding example we're going to see on Friday, I usually don't write my code too much further than maybe something like this. Sometimes I'll write it like that up there. So it's rare that you would see more than just the symbol R in a solution that I would write because it's so easy for me to make mistakes in here. Right? If you only have to get that minus sign in here right once, the probability of you making a mistake went way down than if you wrote that minus sign in this rate, the next rate, and the rate underneath. So usually it's easier to just leave it in terms of R and define those R's explicitly inside MATLAB. But that's what the rate would look like. It would be our terms up there. And of course, anytime we have an ODE, we have to have an initial condition, so C of A of 0 is whatever the initial concentration happens to be. And then we're going to follow that same pattern for all the other species. So this was for species A. We can write it for species B in the same way. So we're going to write R sub B. And the first thing we're going to do is assume that B occurs in every single reaction. So maybe there is B in reaction 1, B in reaction 2, and B in reaction 3. If I look at how I wrote that, I do have some B showing up in reaction 1. I'm going to move this down a little bit so that I can write some of the reactions a little bit more clearly. So if we look at the stoichiometry of reaction 1, what color was I using for 1? Green? Oh, was it purple? Oh, okay, the fuchsia E-pink color. The stoichiometry for reaction 1 says the rate of A in 1 over, it was a minus 1, is equal to the rate of B in 1 over a plus 1, which is equal to the rate of C in reaction 1 over a plus 1. I wrote everything in reaction 1 in terms of A. So if I want RB1, RB1 is going to be equal to minus RA1. B does not show up in reaction 2. Reaction 2 was green. And B, let's see, does show up in reaction 3. And if we write R sub B in reaction 3 over minus 3, that has to be equal to R sub C in reaction 3 over plus 2. But we just so happen to have written R sub B for reaction 3, so we don't really have to change very much right there. So this is just R sub B3. So that's the usual step of writing each one of these. If you wanted to go back and write R sub A1, we have R sub A1. Right? R sub A1 is here, up at the top. We also have R sub B3 down here at the bottom, so you could plug both of those into this expression for R sub A1 here and R sub B3 here. And then the differential for B is the rate of change of concentration of B with respect to time is just equal to R sub B, which is minus RA1 plus RB3. You can again use that sanity check to figure out, is B a product or reactant for each one? Well, according to this expression, B is related to minus R sub A1, and minus R sub A1, according to the way that we wrote our reaction, is a positive quantity, right? We wrote minus R sub A1 is equal to the positive stuff on the right, so therefore we would expect B to be showing up as a product in reaction 1, which it is. Similarly, if we wanted to write R sub B3, like we have down here in red, we would have to look at our rate law, and we find out that we have written R sub B3 as a negative quantity. Right? This term has a negative sign sitting out negative over here, which suggests that B had better be a reactant in reaction 3, which again, it is. It's getting consumed. So the sign of these, right, this one is going to end up being positive because we have written minus R sub A1. And R sub B3 is going to be negative. So B is getting produced in reaction 1 and consumed in reaction 3. And then C goes the same way. There's no difference for C. Well, I mean, there is a difference. I mean, the stoichiometry changes. But the process looks the same. At that point, you dump it into MATLAB and let MATLAB solve all of those when you're done. There is about the only sanity check you can do along the way is this plus-minus business. Right? When you write it down, try to make sure that that thing is showing up as a product or reactant according to whatever that rate is. Once you run the ODE, if you mess up some of these terms as plus and minus, you can still get something that looks like a physically reasonable answer, right? All your concentrations are positive and they're in roughly the right magnitude. There's no millions of moles per liter. So the best sanity check you can do is at this step to say, should this thing be appearing as a product or a reactant in my reaction? And double check that your sign there agrees. And that's it. That's the only way that multiple reactions are accounted for in a material balance. We just add rates for each reaction. Any questions on that point before we introduce 4 pieces of jargon? No? It's just a practice thing. You'll get used to it once you do it a few times. There are a few terms that we use to represent what is a good thing and what is a bad thing in a system of multiple reactions. Species D here will generally mean the desired species. And species U is the undesired species. Obviously, U and D may not appear as the abbreviations you choose to use. You might have to define them afterwards. And because now, unlike CENG 100, CENG 100, we could only look at where did things start and where did things stop. Now we can talk about how do things change in the meantime. Because of that, we have 2 different definitions for 2 terms that you would have learned in 100. The first was selectivity. And the second one was yield. The downside of both selectivity and yield is it depends on who's using them. Even within the chemical engineering field, whether you're talking about instantaneous or overall quantities, people will define yield differently. These are just the definitions of selectivity and yield that we're going to use. So keep in mind that these can be different depending on who's using them. The 2 forms that we have, like I mentioned a moment ago, are the instantaneous form. Come on, pen. There you go. Yeah, I think I got that right. And the overall form. We'll mostly focus on the overall, but you do have a couple of examples. The overall form is denoted by yet another squiggle. It's a tilde over whatever parameter you're interested in. So selectivity is given by the letter S. Oop, sorry. I do it without thinking. The instantaneous selectivity usually gets a subscript to tell you what the desired and the undesired species are. And so the instantaneous selectivity is just the ratio of the rates of the desired to the undesired. If I needed to calculate that somehow in MATLAB, usually at the end of the day you will get a vector of times and a vector of all of your concentrations. It's a matter of plug and chug at that point. You know all of the concentrations. You might have to recalculate those Ks along the way if the temperature is changing, but you have all the equations to do that. There's nothing new here. The overall selectivity, which gets a little squiggle. That's a bad squiggle. That's a fancy squiggle. Is equal to the moles of the desired over the moles of the undesired when the reactor is done, right? Either at some particular time when you just say, I'm going to take everything out after 100 minutes or something like that, or whatever that final time happens to be, that's your selectivity. Yield is similar, but it's only defined with respect to species D. Well, that's not true. It's still defined with respect to a species, but it's not necessarily the undesired. It's whatever your primary reactant is, A. All right, so it varies. If I'm trying to crack a hydrocarbon, then maybe A is whatever hydrocarbon I started with, and D is the hydrocarbon I want to finish with. A is that typical floating definition of whatever happens to be the important species. And the overall yield of D is the moles of D that we finish with over the moles of A that we reacted. One thing that we don't do in this class that we did do in 100 is that we don't typically use selectivity and yield as a fixed parameter. Right? We don't try to design a reactor around a specific yield. We needed to do that in 100 so that we had enough pieces of information that we could actually solve for the extensive reaction. Here, it's more like, given a set of kinetics, what is the yield for that particular reactor? So it's rare that you would see something like, the yield of this reactor is 20%. That sort of a problem statement comes up less often in here. Now it's more like, here's a bunch of kinetics, tell me what the yield is after so and so many minutes. Or tell me what the temperature needs to be to maximize the yield. Something like that. So it's rare that we use these as a problem statement. That's the only bit of terminology that I'm going to introduce for multiple reactions. If you want to read your book, they'll tell you briefly about parallel and series reactions, and then they even define a complex reaction, which is a combination of series and parallel. But none of that is, there's no special set of equations for any of those. It all follows these same features. So briefly, the project. We've only got about 3 minutes, so we'll spend more time on the project when we have time later. But just in case you want to get started, I'll pull it up in a moment, but just so that this keeps recording, you can work in teams of 2 to 6 on the project. I don't care how many people, as long as you're within 2 to 6. There are 2 projects that have been posted. You can pick either one of them. You don't have to do both. The due date for the project is the last day of class. So if you look at the syllabus on the due date, down there on the bottom right, is one for the project. Both of those projects, I'm going to stop recording this now so it's not going to show up because I have to switch to a different software.